Today I'll be presenting on the proteomics, toxicity, and cross-neutralization of the venom of the Samar Cobra or Naja samarensis from the southern Philippines. Snakebite envenomation is an overlooked public health issue in many tropical and subtropical countries. In 2019, it had afflicted 5.4 million people with up to 2.7 million envenoming, which resulted in more than 400,000 long-term complications and up to 100,000 deaths. These astonishing numbers earned snakebite envenomation the status of highest priority neglected tropical disease by the World Health Organization. The WHO plans to reduce physical disabilities and deaths in half by the year 2030. Naja species is a WHO Category 1 venomous snake species of medical importance. Its highest prevalence and mortality is in the regional trio of South Asia, Sub-Saharan Africa, and Southeast Asia. Naja species is endemic to the Philippines, whereby Naja philippinensis is found in the northern aspect of Philippines, and envenomation by this species shows prominent neurotoxicity clinically. Its venom composition is known with a dominance of three-finger toxin at 67%, with subclass short alpha neurotoxin at 45%, with a known species-specific antivenom, PCAV, of Philippine cobra antivenom, which is the only cobra antivenom available in that region. It is monovalent to Naja philippinensis. The lesser known of the two is Naja samarensis, which can be found in the southern Philippines. The venom composition still remains unknown, with prominent neurotoxicity seen anecdotally similar to that of Naja philippinensis, yet with no species-specific antivenom. Now this brings us to our study aims. Naja samarensis was studied using a protein decomplexation strategy utilizing reverse phase HPLC. The fractions was then electrophoretic separated and digested for proteomic analysis using liquid chromatography tandem mass spectrometry. Immunological binding properties between PCAV and venom was done using an ELISA, followed by our aim 3, which is the lethality of venom toxins and neutralization by antivenom. HPLC resulted in multiple peaks, which was divided into 7 fractions. Fractions 1 to 6 was predominantly lower molecular weight of less than 20 kilodalton, which was eluted between the times of 40 to 130th minute. This made up 95% of the total venom composition. Fraction 7 was medium to high molecular weight proteins of more than 25 kilodalton. Tandem mass spectrometry resulted in 31 non-redundant proteins, which was divided into 7 protein families. The venom was dominated by three-finger toxins at 90%, followed by SVMP and phospholipase A2 at 4.2 and 3.8% respectively. Three-finger toxin was divided into multiple subclasses in the Naja samarensis venom. Among these subclasses include short alpha neurotoxin, which is the only alpha neurotoxin present in the venom at 66%. It functions to block the nicotinic acetylcholine receptor at neuromuscular junctions, thereby inhibiting neurotransmission and causing paralysis, resulting in prominent neurotoxicity. The second most abundant subclass under the three-finger toxin family is the cytotoxins at 16.3%. The venom phenotype of Naja samarensis is unique due to the reduced expression of cytotoxin with higher abundance of short alpha neurotoxin. This is clinically relevant as in clinical animation, there is local tissue necrosis is rare with rapidly acting neurotoxicity. PCAV showed high immunoreactivity to fractions 1, 3, 5, and 6. Essentially, fraction 1, which formed the major bulk of the venom proteins, which consisted of short alpha neurotoxin, showed the highest immunoreactivity with PCAV. Fractions 2, 4, and 7 showed moderate immunoreactivity. PCAV exhibited comparable immunoreactivity, implying the sharing of common toxin epitopes between the two phylogenetically related cobra species. In lethality tests, the crude venom and the short alpha neurotoxin, its principal toxin, showed comparable neurotoxicity in vivo, which was highly lethal in mice with an intravenous LD50 of 0.1 to 0.2 microgram per gram of mice. This indicates that the prominent neurotoxicity was due to the short alpha neurotoxin. Hence, we decided to explore the in vivo neutralization of PCAV against these toxins. The neutralization of short alpha neurotoxins showed equipotency at 0.2 mg per ml of antivenom, implying that the alpha neurotoxins of these two species shed conserved antigenicity, which allows immunorecognition and neutralization by the same antivenom. The neutralization potency against the crude venom was lower in Naja samarensis in comparison to Naja philippinensis by about two-fold. This could be due to the higher abundance of short alpha neurotoxin in Naja samarensis venom at 66% in comparison to Naja philippinensis. In conclusion, the three-finger toxin constituted of 90% of the total venom proteins, the highest three-finger toxin abundance in snake venom, with two-thirds being short-chain alpha neurotoxins. The short-chain alpha neurotoxins are exclusively the neurotoxic components accountable for the venom lethality of these cobra species of high medical importance in Asia. The Philippine cobra antivenom was immunoreactive and able to cross-neutralize the lethality of Naja samarensis venom and its principal toxin, but with limited efficacy. Therefore, these findings highlight the need to improve PCAV efficacy and cross-species coverage for a broader geographical use in the Philippines. And these were the references used in this presentation. Thank you.